to the operating system's video-based class. The video belongs to the video series of this course. The content of this video is a summary of the chapter about processes and grids. I invite you to follow the video, study the slides, and read the textbook. The quizzes are given after the video. All students have to send the answers to the question at planned time every week. In the first part of this chapter, we will explore the concept of process, how processes are scheduled in order to gain access to CPU core, some common operation on processes such as process creation and termination. In many cases, processes can interact each other via inter-process communication. There are two mechanisms related to inter-process communication: a shared memory and message passing. The details are given in slide or textbook. The objective of this chapter is to introduce what is the process, the component of a process, and how a process is scheduled to execute with CPU core. The chapter also describes how processes are created from a parent process, or how processes are terminated when they are finished the last statement. The inter-process communication is detailed, and it makes the difference between shared memory and message passing mechanism. Other kind of inter-process communication is implemented using a client-server architecture with socket and procedure call. Let's move on. The first part. Normally, an operating system can execute a variety of programs, including system programs and application programs. The programs become processed when they are loaded into memory. There are multiple parts characterize a process, such as the program code, also called a text session. Currently, activity of a process is described in the program code. It means that the next instruction to be executed with CPU and some processor register. Another section called stack contains temporary data such as function parameter, return addresses, local variables. The data section contains some global variable declared in the programs. The heap section contains a part of memory dynamically allocated during the runtime. So here we can say that program is a passive entity, such as an executable file stored on the disk. Process is an active entity when executable file loaded in memory. So let's see a process in a memory. There are a memory space allocated to a process. So the first section is our text section, the data section, the health and the stack section have a flexible size. So if we check a C program, in a program there are some global variables such as xe. The global variable are stored in the data section. The parameter of a function or some local variable are stored in the stack. So about the memory dynamically allocated to a variable, this memory is stored in the heap section. So in the process execution, the process have to change the states. Firstly, the process is created. It passes to the new state. When this process is chosen by scheduler to execute with CPU core, it's passed to the running state. In the process execution, it may be passed from running to waiting when the process is waiting for some event to occur. If the event are completed, it's passed to the ready state. When the process has finished all statement, it can terminate it. Here is a diagram of process state. So the operating system manages processes by association on process information in a process control block PCB, or sometimes called task control block. In a PCB, there are some information about process state, process number, program cover, CPU register, and so on. So how about read? Until now, we assume that process have a single rest of execution. If in many programs there are multiple locations of the program can execute at the same time, the operating system can create multiple program cover per process, can have a storage for read. So read is the mechanism of control multi-location execution. To maximize the CPU use, the operating system can switch processes quickly on CPU core. So process scheduler select one process among available process for the execution on CPU core, following according to an algorithm. So here, the operating system can maintain many scaling curves for processes. A ready curve contains a set of processes residing in main memory and ready to execute. The await curves contain a set of processes waiting for an event to be complete. So the CPU switch from process to process, we call a context switch. A context switch occurs when the CPU switch from one process to another process. Here is an example of context switch between process P0 and process P1. So context switch is an overhead. The system there is no uniform work while switching. Operations or processes include process creation, process termination. A program loaded into a memory becomes a process, and this process can create other processes called children processes. Each process can be identified and managed by operating system via a process identifier (PID). A system can be viewed as a tree of processes. What are we interested here? How the children processes use parent resources, address space, and how is their execution related to a parent execution. There are some options for resource sharing. Parent and children share all resources, or subset of parent resources, or no resources. The execution of parent and children processes can be concurrently, or the parent process waits until children terminate. Regarding to arrest space, the children processes usually duplicate the parent arrest space and load programs into it. Process termination. Process terminate when it has finished the last statement. Before termination, all children processes return status data to parent. After termination, the resources of this process are deallocated by operating system. Some operating systems do not allow children processes to exist if their parent had terminated. If no parent waiting, process is a zombie. If parent terminated without invoking wait system call, process is an orphan. Okay, inter-process communications. Process within a system may be independent or cooperating. Some processes need a cooperation for information sharing, computation speedup, or sometimes just for convenience. Processes cooperate by inter-process communication using two models: share memory and message passing. Two processes may share the same region of memory, or two processes may communicate by exchanging messages with one another using message passing. So, a summary for the first part of this chapter. Firstly, a process is a program in execution, and the status of the current activity of a process is represented by the program caller, CPU register, or some information stored in the PCB. The layout of a process in memory is represented by four different sections: the text section for program, the data section for global variable, a heap and stack section for temporary data, and memory dynamically allocated. As a process executes, it changes state. There are generally four states of a process: ready, running, waiting, terminating. When a process is newly created. A process control block is a kernel data structure that represents a process in an operating system. And the role of the process scheduler is to select an available or ready process to run with our CPU. An operating system performs a context switch when it switches from running one process to running another. So, when shared memory is used for communication between processes, two or more processes share the same region of memory. If two processes may communicate by exchanging messages with one another using massive spacing. So continue for the second part. In the second part of this chapter, we will explore the RAID concept, the multi-core programming, and some modules for multi-threading. This chapter also presents common thread libraries. The objective of this part are to introduce the motivation of thread usage, components of a thread, and contrast the threads and processes. Some benefits of designing multi-threaded applications are presented beside the challenges. An application composed of many tasks. These tasks can be implemented by separate threads such as update display, fetch data, spell checking, and answer a network request. These tasks are also implemented by processes, but the process creation is heavy weight. The threads run within an application can increase efficiency. Let's see the difference between a single-threaded process and multi-threaded process. The threads belonging to the same process share the code, data, or often file paths, and each process is characterized by separate program caller, BC, registers, and stack subsection. An example of multi-threaded application is web serving. The web client browser makes a request to a web server for a page, and the web server process can create a new thread to service the client request, and this process can resume the listening for additional client requests from other browsers. So, multi-core programming. Modern systems are multi-core and multi-processor now. So, application programmers should explore the system complexity. They confront challenges such as how to divide activities or tasks, how to get the balanced execution, how to split data, and data dependency. Here, we can distinguish two concepts, parallelism and concurrency. Parallelism implies that a system can perform many tasks simultaneously or in parallel. The concurrency makes multiple tasks progress, but only one task executes at a time. Single core or processor can only provide concurrency. Let's have a closer look at concurrency and parallelism. In a single core system, the tasks T1, T2, T3, T4 progress during time evolution, but each task executes with a CPU core at an instant. Regarding to multi-core system, T1 and T2 or T3 and T4 execute in parallel on core 1 and core 2. More detail on multi-core programming are presented in slide and textbook. So, multi-threading model. There are two kinds of threads, kernel threads and user threads. Operating systems use 3 types of module for the mapping from user threads to kernel threads. The many-to-one model maps many user threads to a single kernel thread. Fewer systems currently use this model because this model implies that Multiple threads may not run in parallel on multiple systems. The one-to-one model maps each user thread to one kernel thread. The model is used by most common operating systems. The many-to-many model maps many user threads to many kernel threads. So, some thread libraries such as Pthreads, Windows multi-threading, Java threads provide Brom with API for creating and managing threads. The threads can be implemented. Library can be implemented in user space or at a kernel level, supported by operating system. Let's continue to study with the slides and textbook. Try to get completed with keys for this chapter. Thank you and goodbye.